So this is the video for buffer solutions and titration curves. So there's not going to be too many, there's absolutely actually no calculation questions from this section. There will be probably a question dealing with what a buffer is made of, how does it work, etc. So we recently, in the last video, we talked about how acids have their conjugate bases, which are often present in salt form. So we know that acetic acid, for example, has a conjugate base. So when you add it to water, you get acetate ion. The problem is, like, you can't really have negatively charged particles just existing on their own. They always pretty much form salts with other positively charged ions. For example, that's like saying instead of sodium chloride, NaCl, I'm just going to buy like Na+. Na+ by itself doesn't, like, you can't buy that anywhere. You can't produce that or add just that to a solution because it's not available. It always naturally occurs with some positively charged ion to balance the charge, so it's overall is neutral. So there's like you can think this is just like an NaCl salt. There's electrostatic attractions between the ions, which kind of stabilizes the structure. Same way with ammonia, its conjugate acid will be NH4+, and NH4+ doesn't exist on its own. It exists as NH4+ Cl-, right? So, or Br- or I-. Whatever exists here doesn't really matter because, I mean, for the purposes, we want to focus on the NH4+. So you can add any negatively charged ion that you would like, but essentially it won't contribute. It's just there to balance the positive charge, and we can ignore it in terms of the buffer solution, if you will. So the solution that contains a weak acid conjugate base mixture or a weak base conjugate acid mixture. So again, this is a weak acid and this is its conjugate base, but it's always present, or it's sometimes called conjugate basic salt, right? Because this is a salt which is basic, like we went over last time. The same way, we have a weak base plus an acidic salt or a conjugate acid mixture. That's called the buffer solution. Basically, if I have ammonium and ammonium chloride in water, I have ammonia. Sorry, if I have ammonia and ammonium chloride, I have ammonia and ammonium in solution. This chloride is just a spectator ion, does not count for anything. So buffers, what do buffers do? They resist changes in pH. So that's what they do, and we're going to talk about how they resist changes in pH. Right? So we have a area or a region here that addition of acid or addition of base does not change the pH until the buffer breaks, basically, or the capacity of the buffer is exceeded, after which there is a sharp rise or sharp drop in the pH. Again, so this is what I was saying last time, weak acid and salts, weak base and its salts, which essentially translates to weak acid conjugate base, weak base conjugate acid. And these are the exact examples that we saw last time. Oops. So this is how buffers do resist changes in pH, and this is can be basically explained by Le Chatelier's principle. So let's look at this equilibrium here. So we're considering that the acetate ions are present in solution, and acetic acid ions are also present in solution. So when I have a buffer solution, I have this present, I have this present, and so more or less, you will notice that this equilibrium is kind of weird because it's written the other way around. Like, usually you would write the equilibrium that way. So we're just gonna, ignore that for a little bit. We're gonna go to our PowerPoint where it's in a more what's the word? Comfortable format, I think, to look at, so that you're not, kind of wondering, oh, why is it written the other way? It doesn't really matter. But we'll look at it here. So again, acetic acid is a weak acid. It produces very little acetate ions, so there's not much acetate ions from the dissociation of acetic acid because this is a weak acid, right? But then we add extra acetate ions, so we're adding extra ions of acetate, which increases the acetate concentration and therefore drives the equilibrium further backwards, right? If we increase the products, we're going to shift towards the left. And so basically we have almost all our acetic acid that we added, and we have almost all our acetate that we added. There's very little of any type of reaction going on, so to speak. There will be a little bit of H3O plus present because essentially, even if they have equal concentrations, the Ka of acetic acid is greater than the Kb of acetate ions, and so therefore this will dissociate more for whatever little that's worth and produce a little bit more H3O plus. But again, it's an acidic buffer because you have a weak acid and its conjugate salt, conjugate basic salt, right? So you'll have a lot of acetic acid, you'll have a lot of acetate ions from the sodium acetate, you'll have just enough hydrogen ions to make the solution acidic or below 7, and then you have, water and sodium, which is not really, we don't care about those. Again, just a brief reminder of why we don't care about sodium, because it reacts with water to give NaOH, but wait, it doesn't actually do this reaction because you can't form NaOH. This equilibrium lies all the way to the left, so we'll just stick with the Na+. In short form, it doesn't matter. So, if we write our equilibrium expression again, let's see what happens when we add OH minus to the solution. If I add OH minus, they're going to combine with the H3O plus, so they're going to decrease my H3O plus, which therefore you're basically trying to make the solution more basic, right, by adding an OH minus. But because I decrease H3O plus and my acetic acid can basically dissociate to shift that equilibrium back to form more H3O plus. So any decrease that I do is immediately countered by this equilibrium setup. So the buffer essentially can only break when I run out of acetic acid to actually dissociate. So that's when my buffer is going to you're gonna stress it out so much beyond its limits that it cannot resist the change in OH minus anymore. But until then, you're adding OH minus, which is combining with your H3O plus. You're making it more and more basic, or you're trying to make it more and more basic, but the reaction is going towards the right and it's making it more and more acidic. So the reaction counters by becoming more acidic, and therefore your buffer is not changing that much. Right? It will rise a little bit, but not substantially. And very similarly, we have a weak base, we have ammonium, and then we add ammonium chloride. Again, the chloride doesn't really react with water in any substantial manner because you can't form HCl as a product. And therefore, you're adding extra ammonium ions. And again, you have ammonia, you have ammonium ions, you have just enough hydroxide ions to make it a basic solution, and then you have other stuff, whatever. So let's add an acid to this buffer. We didn't talk about the acid case for the previous one, so we'll talk about both. Over here, NH4 plus OH minus. So again, adding acid would combine with the OH minus and reduce the OH minus concentration, which again, you're trying to make it more acidic by adding acid. But this reaction will shift towards the OH minus to counter that change and therefore make it more basic. So finally, like the net pH change will not be that much. It will reduce a small amount, but not significantly, right? The same way we can even consider what happens if I add OH minus. So if I add a basic solution, if I increase the OH minus concentration, I'm trying to make it I'm trying to make the solution more basic, but my reaction, because I'm increasing product concentration, will shift to the left or towards the reactants, which makes my reaction is going to shift to a more acidic stance, and therefore those basically cancel out. I'm adding OH minus, so I'm trying to make it more basic, but the reaction shifts so that it becomes more acidic, and therefore, or I should say less basic, because there's no H3O plus. More acidic is the same thing as less basic, right? And so they will cancel out, and then you won't have any substantial pH change finally, right? It's important, buffer solutions are important in biological systems such as the blood, just because enzymes, you've heard of enzymes, hopefully, they are basically proteins that exist throughout the human body that catalyze reactions, or without enzymes, reactions would not be possible. And if reactions are not possible, then, well, we would be in a lot of trouble. And therefore, these enzymes, because of their protein structure and because of the protein having a lot of amine groups, which are NH2 groups, they can easily be protonated and deprotonated, and this changes their structure, right? So the pH is extremely important for a protein, because beyond plus or minus that pH, it's going to change how this protein folds and how it looks, or how this enzyme folds and looks, and therefore change the products, or maybe make the reaction unable to work. And so there's optimum pH levels for each enzyme, and that's why, our stomach is acidic, but our intestines are basic, because the enzymes in the stomach work best in an acidic medium, and the enzymes in the intestines, whatever, work best in a basic or alkali medium. And therefore, our pH range in the blood is essentially between 7 and 7.5. Above this or below this causes severe problems because of important reactions not occurring in our body. So that's just one application of buffers. Again, we have cosmetic products, shampoo to counter out alkalinity of soap. Never heard of that before. But again, there's a lot of places where pH is important. And so 411, question 4 to 6. I'm just going to see what's on page 411. That's the next page. Describe how a buffer solution differs from an aqueous, acidic, or basic, because it has its acid plus a conjugate basic salt, or a base plus a conjugate acidic salt, right? It just, the presence of the conjugate is how it differs. Importance of buffers in blood, we just mentioned enzymes react, important, NaCl and HCl does not act as a buffer because, even here I should have added, it's always a weak acid, a weak base, and its conjugate salt. HCl would dissociate completely in water to form H3O plus. However, NaCl, because Na plus and Cl minus are conjugates of strong bases and acids, they will not react in water, so you won't have that kind of equilibrium where you have both reactants and products to kind of balance the change. You won't have that situation, and therefore this does not act as a buffer. So that was kind of easy, just because you don't have an equilibrium that can shift back and forth present when you have strong acids and bases. Okay, I'm going to quickly go over titration curves because this is closely related to buffers. So here we have a strong acid, strong base titration, where basically you have, again, here you're starting with the strong acid, right? Because your starting pH is very low. You slowly, you don't have much change in your pH, because all this while your OH minus is countering your H3O plus, but because it's a strong acid, your H3O plus remains dominant, and that doesn't affect the pH too much. But as soon as you kind of, again, this is just from 2, but as soon as you kind of hit the equivalence point where your moles of acid equals moles of base, you have a sharp increase in pH. So there's no between basically the important level from like 3 to around 11, where you might want to modulate your pH, there's absolutely no buffer. So it just goes from 3 and like 1 milliliter later, it shoots up to 11, right? So there's not much of a buffer zone there. And that makes kind of sense because you're having a strong acid, strong base, and like we just mentioned, those don't have the equilibrium set up to accommodate pH changes. And so we learned the difference between equivalence point, where the number of moles of acid equals number of moles of base, and then what we call the end point of the titration, where there's an actual color change from your indicator. And because, phenolphthalein and methyl red both don't have endpoints near the equivalence point, but because it's a strong acid, strong base, and the volume added is going to be less than a drop, that difference is not going to matter because that's close enough. So the pH at 7 will be almost indistinguishable from a volume standpoint from pH 8 or 7.8 or wherever phenolphthalein changes, or 5.6 wherever methyl red changes. Right, so there is a difference between equivalence point and end point, but it's not major in this case because you have that sharp rise in pH. Here we have a weak acid, strong base. So you're starting off again in an acidic kind of solution with your weak acid. You're adding a strong base, so your pH is going to increase up till its max here. But you can see here as it's increasing, the sharp rise is not that significant in terms of is not that significant. It's not that big compared to our previous case, or strong acid, strong base. You have a lot of what we call buffer region. So between the pH of in between, 3 and 7 or 3 and 11 even, wherever this is, 3 and 12, you have this region where you're slightly increasing pH, but not significantly. It's not a sharp increase until you get to pH 7. Right? pH 8.8 is the equivalence point. So basically what you have to know for a weak acid, strong base, it has a acidic buffer region. Again, just because when you're adding the strong base, you have a weak acid, I'm not adding that, but and an acetate ion both present in solution. And this sets up the buffer system for which can essentially buffer the pH here. So it has an acidic buffer region, and it has a equivalence point that is basic, because when you have, again, you're adding, let's say, sodium hydroxide to acetic acid at equivalence point, these are going to be equal to each other, but you still have this guy, which is going to be a basic, which is going to act as a base basically, and therefore you have a basic equivalence point. You'll get a basic salt being produced, Na+, right? And therefore that causes the equivalence point to be basic, and so we have to use phenolphthalein as an indicator because that end point is very near the equivalence point. The exact opposite for a weak base, strong acid titration. You start off basic, you have a buffer region that is basic, but you have an acidic equivalence point, and you would use methyl red as an indicator. Again, because at equivalence point, these two are going to be equal, but the reaction is basically going to produce NH4Cl, where this is contributing to the acid, or this is an acidic salt, and so therefore the pH will be acidic. All right, so next is basically going to be the titration questions, all the way calculating pH at equivalence. So we're going to do that, and then we're going to finish off with KSP. See everybody in class.